Bismillahirrahmanirrahim. Assalamu alaikum. Dear students, I welcome you all in this course on data communications and computer networks. This course is being offered at the Department of Computer Science, ComScience, University Islamabad, Lahore campus. This is our lecture number 3 of asynchronous mode of learning in phase 2. In today's lecture, we'll talk about TCP congestion control mechanisms and TCP congestion avoidance, TCP additive increase and multiplicative decrease mechanism, fast transmit and fast recovery. So why do we need to have a fast recovery, and what are the different TCP variants? We'll also be talking about TCP timers. The learning outcomes of today's lectures are, at the end of this lecture, you should be able to understand TCP congestion control and avoidance mechanisms and its variants. You should be able to critique loop transmit and fast retransmission mechanisms, and you should be able to argue that why do we need to have a fast recovery mechanism in place. You should be able to investigate the variants of congestion control mechanisms. So before we start discussing today's lecture, let me quickly give you an overview of what we covered in the last lecture. So in the last lecture, we talked about flow control mechanisms of TCP and the problems with the flow control mechanisms such as sliding window and especially the interactive applications where we are sending small size segments, so how we can counter such problems with the flow control mechanisms. And then we talked about the connection establishment mechanism of TCP, the three-way handshaking mechanism and its vulnerabilities and its possible solutions. And then we also introduced ourselves to TCP congestion control mechanisms. And in TCP congestion control, there were two approaches that we introduced ourselves to. Number one, end-to-end congestion control mechanism, and then network-assisted congestion control mechanism. Since TCP makes use of end-to-end congestion control mechanisms, so today we'll talk about TCP congestion control mechanism in detail. But before discussing TCP congestion control mechanism, let's quickly talk about what do we mean by congestion and what are its causes and implications, and why congestion is bad. And let us try to raise some questions that will be discussing in this lecture while discussing congestion control mechanism. So we started discussing this concept in the last class. So what is congestion, and why really we are interested in discussing congestion, right? Means, what do you think? What gives rise to congestion? So the answer is very simple. So we will experience congestion when the offered load is greater than system capacity. This means what? This means we are sending too much data. For the network as opposed to receiver to handle. So we are sending too much data for the network that it can handle. So this will result into a congestion. But the next question is, what are the causes and the implication of congestion? So what are the causes and implications of congestion? Why congestion exactly happens? So one of the causes that packets are arriving faster than a router can forward them, right? So packets arriving faster than a router can forward. So if a router is not able to forward a packet, why? Because packet's arrival rate is faster than the processing rate of the router. So what a router will do in this case? Yes, routers in the network queue packets. So there are queues in the router. So we place packets in the queue that cannot serve immediately, that they cannot serve immediately. So, so what's the problem in doing so? So there is a possibility. There is a possibility that if queue overflows, packets are dropped. I mean, what if there is no space in a router? So if queue overflows, what will happen? Yes, you're right. Packets are dropped. Packets are dropped. But what's the problem in such a case? Because if packets are dropped, there will be more retransmissions, right? And this will add more into the congestion. And there's also a possibility that queued packets experience delay. What if you're waiting, but a packet is waiting inside, a network, and it is experiencing a delay? This might also result into a retransmission, adding more into the congestion. So, what's the consequence of having a congestion? Why we really are interested in discussing congestion control mechanisms? So for that, we need to understand the consequence of congestion. So the next thing that we want to discuss is consequences of congestion. So if a queued packet or queuing delay, what if queuing delay? By the way, this queuing delay is the time that a packet has to wait inside the queue for its turn, is greater than RTO, retransmission timeout. So this is retransmission timeout. And retransmission timeout, RTO, basically triggers a retransmission or automatic repeat request. We are familiar with this concept, right? We have covered it in the earlier lectures. So, and obviously this retransmission timeout is calculated based on round trip time that we'll be discussing in detail in today's lecture. So if the queuing delay is greater than the retransmission timeout, so what will happen? Obviously, the sender retransmits packet because sender is waiting for an acknowledgement and the packet is still inside waiting at a router, and the delay is more than the retransmission timeout. The timer is, and the timer expires, we automatically resend retransmits. So sender retransmits packets. And why this is not good? Yes, this is not good because it is adding to congestion. So there is already a congestion in the network. We are sending data at a rate faster than our router can process. So if there are more retransmissions, this means there will be the congestion will increase. And second consequence of congestion might be that if the queue size is full, this means packets are being dropped. So dropped packets also lead to more retransmissions. And what's the problem with this retransmission? Yes, you're right, because this will add further to congestion. And if this is not handled, the congestion is not handled, we might, or the network may result in a congestion collapse. Okay, means the network throughput has been significantly compromised. So that's why we really need to, we really need to come up with some congestion control mechanisms. But in order to, talk about different congestion control mechanisms, so we should be keeping in mind that there are certain constraints in, developing a congestion control mechanism. So constraints, especially when we talk about this end-to-end congestion control. Okay, so there are constraints like decentralized control. The control is decentralized. Means every machine, a host, and host will be controlling the congestion. There is no centralized mechanism for that. So decentralized control. So this is a challenge with how the individual nodes will be handling congestion. Then, unlike routing, no local reactions at router. Other than, I'm talking a scenario beyond buffering and dropping. And then we have long feedback time. Either the receiver will identify that a packet has lost, right? Or by sending duplicate acknowledgement, triple duplicate acknowledgements, or we will have to wait for the expiry of this retransmission timeout in order to retransmit a segment in order to identify that a congestion has happened in the network. And the most important one is dynamic network conditions. What do we mean by dynamic network conditions? We want to say that a connection, dynamic network conditions means a connection or connections come and go. So the network is very dynamic. We are having new, connections, and we have to control the congestion in the network based on that. So before we really start looking into network congestion, so I would like to identify a few questions that we'll try to identify the answers of during this lecture, right? So number one, the first question that we need to answer is that how to determine that there's no congestion. And if there's no congestion, then by how much, because if there's no congestion, we need to increase our sending rate. So by how much do we increase sending rate? Because sending rate is linked with, in a minute we'll see, with congestion window. So how are we gonna increase the congestion window? How much, right? So if there is, so first question is, and how to determine that there is no congestion in the network, and if there is no congestion in the network, so we really need to increase our sending rate, and we can increase our sending rate by increasing the congestion window. So then we need to identify that how much do we need to increase the congestion window. Then the third question that we'd like to answer is, or try to find the answer is, how to detect congestion. So how would we know that a congestion has happened in the network? How to detect congestion. So if a congestion has happened, the next question is, we also need to decrease congestion window now, because we need to slow down the sending rate, because why the congestion will happen? Yes, we have discussed in the beginning that a congestion happened because we are sending data more than the capacity of the network, right? So if a congestion has happened, so we need to answer by how much. By how much must congestion window be decreased? Okay, so these are the questions that we will try to answer in today's lecture while discussing congestion control mechanism. So come back to this TCP congestion control mechanism. Let's have the overview. So TCP's congestion control mechanism is end-to-end congestion control, means there is no network assistance involved. Routers are not sending any choke messages or explicit congestion notifications in this case. So this means that a sender needs to limit the number of packets in the network to window W. So what a sender does is it maintains a variable called window, and this window is, by the way, this window is minimum of either the receive window. We are familiar with this receive window size. This is advertised by the receiver in the TCP segment header, okay, or the floor of congestion window, right? So or floor of congestion window. So whichever is the minimum will identify the window, the size of the window, right? So the center maintains a variable window which is minimum of either the receive window or the floor of the congestion window. In the beginning, so this will be advertised by the receiver, but this congestion window in the beginning is initialized to 1. This is initialized to 1 maximum segment size. Okay. So initially, the size of congestion window is 1 maximum segment size, and we know this maximum segment size depends upon maximum transmission unit size. So by using this variable window, sender can roughly calculate its sending rate. So the sending rate is equal to window, which is minimum of either the receive window or floor of congestion floor function, floor of congestion window, and the initial size of congestion window is 1 is equal to 1 maximum segment size. And if we divide it with RTT, round trip time, it will give me the number of bytes per second a sender can transmit. Okay, and for example, if I assume, so we can easily calculate it. For example, if I assume that the congestion window or the maximum segment size is So if I assume that MSS, maximum segment size, is 500 bytes, and let's assume that RTT is 200 milliseconds. So what will be the sending rate? Yes, we'll divide the maximum segment size, 500 bytes, with 200 milliseconds. So the sending rate would be 20 kilobits per second. Right. So with this maximum segment size and with this round trip time, the sending rate of a sender would be 20 kilobits per second. Okay. So we can clearly see that this is pretty much, this is very dynamic, right? W is dynamic, window is dynamic, because if there's a congestion in the network, we have to either decrease the congestion window, right? And if there's no congestion in the network, we will be increasing it. We'll see in a minute how it is done. So this means this rate will also be dynamic and will be based on the network congestion. By the way, sender may not exceed the minimum of the congestion window and receiver window and controlling its sending rate. Okay. So TCP's congestion control mechanism is basically based on slow start, additive increase, and multiplicative decrease. Multiplicative decrease. So let's talk about the first important part of TCP congestion control mechanism, which is called slow start. So a slow start means the TCP will be sending data at an exponential rate upon receiving an acknowledgement before reaching to an equilibrium, right? So this we can understand that with this condition, so we can say that while while congestion window is less than equals to slow start threshold. So here TCP congestion control mechanism maintains a couple of variables. One is the congestion window, and the second is this SS thresh, which is slow start threshold, right? So if while the congestion window size is less than equal to slow start threshold, what we'll do is we will increase congestion window exponentially, right? So this means new congestion window is basically calculated by the previous congestion window, and this will do for every act, for every acknowledged congestion window. So we will be in a slow start if the congestion window is less than equal to the slow start threshold. And by the way, this slow start threshold's initial value is 64 kilobytes. Okay, So initially its value is set to 64 kilobytes. So if the congestion window size is, and we know this, we have just covered this in the previous lecture, that the initial previous slide, that the initial congestion window size is 1 MSS, maximum segment size. So while the congestion window size is less than equal to slow start threshold, what we'll do will increase the window size exponentially for every acknowledged congestion window, right? So initially, as we have discussed earlier, that the window size is equal to 1, right? So this window size is equal to 1. This 1 is, by the way, what? 1 maximum segment size. Okay. And what we'll do, we'll transmit one data segment. And upon receiving its acknowledgement, right? So we will increase on each successful acknowledgement, we will increase window size by 1. So this means next time, how many number of segments I'll be sending? Yes, you're right, 2. And now if I receive another acknowledgement, so next time I'll be sending how many number of acknowledgement? How many number of segments? Yes, you're right. Okay, 3. Then if there's another acknowledgement, I will increase its size by 1. Okay, but this is happening on each successful acknowledgement. But in each RTT, so this is one RTT. In each round trip time, its size is doubled, right? So after every RTT, upon receiving a successful acknowledgement, the size will be doubled until we reach slow start threshold, right? If the congestion window now is greater than or equal to slow start threshold, we will enter into this additive increase, which is called CA or congestion avoidance phase. Okay, so the first phase of TCP congestion control mechanism is this slow start mechanism, where we'll see if the congestion window is less than or equal to slow start threshold, and the initial value of slow start threshold is 64 kilobytes. What we'll do, will increase this window size exponentially after each RTT, right? So here we can see that this window size is being increased exponentially, and then we will keep doing it until we reach a congestion avoidance phase. So this CA is basically congestion avoidance phase. And if we are in a congestion avoidance phase, so what we're going to do is we will increase it linearly. I mean, additive increase is happening after that, right? So when I'm saying that, what does this mean? This means, okay, what does this congestion, what does this congestion avoidance phase means? That while congestion window is greater than a slow start threshold, what we'll do, we'll increase congestion window linearly, right? So it will be an additive increase, okay? And that we will be doing for every acknowledgement, right? For every congestion window fully acknowledged, right? Or full of acknowledgements. Okay, and we'll keep doing it until we experience a a timeout or triple duplicate acknowledgements that we'll see in a minute. Okay, so what happens in the congestion avoidance phase? So in congestion avoidance phase starts when the congestion window size is greater than or equal to the slow start threshold. The slow start threshold initially is set to 64 kilobytes, and on every successful acknowledgement, what we are doing basically, we are increasing its window size linearly. Right? So linear growth of window upon receiving every acknowledgement or after each RTP. So clearly, if here, one segment is transmitted and we receive acknowledgement, so next time we're increasing it back to, and then so on and so forth, right? So this is how we increase the congestion window. Remember, um, we raised a question that how to identify how much to increase the congestion window size if there is no congestion in the network. So if we have not reached the slow start threshold, so we'll be increasing the congestion window size exponentially. But if we have reached the slow start threshold, then we will be increasing congestion window size linearly. We will be probing the network pipe or bandwidth until we come across segment loss or triple duplicate acknowledgement. So what happens in additive increase is that we are increasing the window size by 1 in the absence of a loss event or triple duplicate acknowledgement. But when there is a loss event, I mean, the RTO has expired and we have not received an acknowledgement, what will happen? So we'll enter into multiplicative decrease phase. In this multiplicative decrease, what is happening is that we will decrease the slow start threshold by dividing the congestion window by 2, and then we'll go back into the slow start phase. Means we'll start with congestion window size 1, and then we'll exponentially increase its size. So how we detect a packet loss? So there are 2 ways in which we can detect a packet loss. We can interpret packet loss as a congestion signal. Okay, so there are 2 options here. The option number 1 is that we are waiting for a timeout, but this can be long, obviously, right? So this option means that we will interpret packet loss as congestion signal if retransmission timeout has expired, right? And on the other hand, we have a fast retransmit mechanism also, and this depends upon the receipt of triple duplicate acknowledgement. So if retransmission timeout has expired, or the sender is receiving triple duplicate acknowledgement, this means our congestion has happened in the network, right? So there's a packet loss that we need to react. Okay. So if there is a triple duplicate acknowledgement, so we will not wait for the RTO to expire. So in this case, in the case of fast retransmit, we will not wait for the RTO to expire. Upon upon receiving 3 duplicate acknowledgements, we will immediately start sending the segments, and obviously before that we will adjust the slow start threshold by dividing the congestion window by 2, and we'll again enter into the slow start phase. The motivation behind this is why we want to do with this fast retransmit, not why we don't want to wait for for RTO to expire, because waiting for a timeout is quite long, right? So the motivation behind it is to do a fast retransmission rather than waiting for RTO to expire. With fast retransmits, with fast retransmit, TCP can retransmit after 1 RTT. Obviously, instead of waiting for retransmission timer to timeout. Okay, so we do not wait for RTO to expire. So as soon as we receive 3 duplicate acknowledgements, we quickly enter into a fast retransmit mode and we start sending the data. So let's try to understand all these concepts with the help of this diagram. So this has the slow start phase here. Then we have congestion avoidance, and then we have this timeout event, and then and then we see how we gonna retransmit and just our sending rate. And hopefully this should answer all of the questions that we raised initially at the start of the lecture. So, by the way, there are different TCP variants, and at the moment I'm talking about TCP Tahoe. Okay. So what happens here is that we start with maximum segment size. So this is the congestion window, and these are the number of transmitted segments or transmission rounds on x-axis. So remember, the initial congestion window size is, yes, you're right, 1 maximum segment size. So initially we transmit 1 maximum segment size, and upon its receiving its acknowledgement, we double the congestion window size. Now we'll be sending how many number of segments? 2. Upon receiving the acknowledgement, cumulative acknowledgement for this segment, we'll be sending 4 segments. So congestion window size is now 4. And upon receiving cumulative acknowledgement for these 4 segments, I will increase the congestion window to 8. And upon receiving cumulative acknowledgement for these transmitted segments, I will increase the congestion window to 16. So here you can clearly see that this increase is exponential. 1, 2, 4, 8, 16, and now we have reached to threshold. Let's assume that the threshold was, for this example, yes, we know that initial value of the threshold is a slow start threshold is 64 KB, but just for the example, let's assume that we have reached the threshold, and threshold was 16 segments. Okay, so this threshold is obviously, we know this is slow start threshold. Okay, so size is 16. So this is what? This is the initial phase. Remember, we said TCP has the slow start, additive increase, and multiplicative decrease. So this phase is representing the slow start. After reaching at the threshold, now we will be increasing the congestion window size linearly, okay? I mean additively. And this means we are in congestion avoidance phase, right? This is additive increase. Additive increase. Okay, and you can think of this point as the system is operating at need. Okay, so now we will be increasing a congestion window size linearly. Upon receiving the acknowledgement at this point, the congestion window size is 17. Upon receiving acknowledgement, cumulative acknowledgement, the congestion window size is 17. Again, receiving acknowledgement, the congestion window size is 18. And now, after receiving the acknowledgement, congestion window size is 19, and then congestion window size is, say, 20. And let's assume this is the cliff, right here. I mean, this is the point where we experience a timeout. Here, the RTO has expired in wait of an acknowledgement. So what we're going to do is, so first of all, straight away we would adjust this threshold, the slow start threshold, by dividing the congestion window by 2. So what was the congestion window size here? Yes, 20. And now we'll divide it by 2, and the new threshold is 10. And we'll again go back to slow start phase. Means we'll start with congestion window size 1, where the congestion window size is 1 maximum segment size. Upon receiving the acknowledgement, will again, increase the congestion window size to 2. Upon receiving the cumulative acknowledgement, will increase its size to 4, then 8, and then 10. And then again, we will try to probe the network, the bandwidth or the pipe here. Okay, so this is one way we can trigger retransmission. But there's another way where we can trigger retransmission, and that is upon receiving triple duplicate acknowledgement. So if we're receiving triple duplicate acknowledgements, so this means we will not wait for the timer to expire, and we will immediately do the same thing. That is, we'll do the multiplicative decrease. By the way, this step here, this step is known as multiplicative decrease. Okay, right. So we have decreased the window size or the threshold by dividing the congestion window size by 2, and then we are into slow start phase again. So we do not wait for the expiry of the retransmission timeout, and immediately upon receiving triple duplicate acknowledgements, we reduce the threshold, slow start threshold, by dividing the congestion window size by 2, and then we again enter into the slow start. But there is a problem with this approach, or with this TCP Tahoe. That is, we are not really filling up the network pipe or the bandwidth. Even in the case of this fast retransmit, the action upon receiving this triple duplicate acknowledgement is fast retransmit. Okay. Still we are wasting the bandwidth because of the loss of segment, right? Yes, we are sending it fast, but still it's not, filling up the network pipe or the bandwidth efficiently, right? And the solution to this problem was introduced by Wen Jacobson by adding fast recovery with fast retransmit. So Wen Jacobson proposes in 1990 that a fast retransmit should have a fast recovery mechanism also. That is, the TCP is required to generate an immediate acknowledgement, obviously, on receiving triple duplicate acknowledgements when an out of segment is received, to inform the sender that a segment number, what segment number is expected. By the way, it's important for us to understand that why a receiver will be sending triple duplicate acknowledgement, and there can be following reasons behind this. Number one is maybe a segment has lost, or maybe the segments are reordered, or maybe the data is still flowing between the two ends. Okay, so these are the possible reasons that a receiver will be generating triple duplicate acknowledgements. So now, if a triple duplicate acknowledgement is received, means 3 acknowledgements are received in a row. So this means we will definitely enter into a fast timeout, a fast retransmit mode, and will not wait for the timeout. But we'll do congestion avoidance, but not the slow start. So this means we will not go back to 1 again, where this congestion window size is 1 maximum segment size, and then again we increase it exponentially, right? So we will not go in this slow start phase, and we'll try to do a catch up, right? We will try to increase the congestion window size so that we can efficiently utilize the network bandwidth. And this was proposed in a variant of TCP known as TCP Rto. The picture that we have in front of us is representing TCP Rto. Okay, so in TCP Rto, this phase is the same, right? So this phase is slow start. So remember, we start with maximum segment size, congestion window size having or equal to 1 maximum segment size, and upon receiving acknowledgement, we increase the congestion window size to 2, and upon receiving cumulative acknowledgements, we receive it to 4, and then 8, and then 16. So this increase is exponential, right? And belongs to, and it represents the slow start phase. And then we have this now when the congestion window size is equal or greater than the slow start threshold, which is 16 in this case. Now we will increase it linearly, right? And now we are increasing it linearly from 16 to 17, 18, 19, right? And 20. And let's assume that now at 20 we receive triple duplicate acknowledgement. So these are the triple duplicate acknowledgements. Acknowledgement number 1, duplicate acknowledgement number 2, duplicate acknowledgement number 3. So now we'll do the multiplicative decrease. So this step here is the multiplicative decrease. That is, we will divide the congestion window, which was what? 20 by 2. And the next, and by doing so, we'll get the slow start threshold value, which is obviously 10 in this case. But we do not enter into this slow start. And what was happening previously? We were in this slow start. We were sending segment number 1, and then segment number 2, and then segment number 4, and then segment number 8, and then segment number 10. Now this is not happening here. Okay. Why? Because this is fast recovery. Now this mechanism is called fast recovery. How? Because we do not enter into this slow start. Now, what is the congestion window? The next question is. So the congestion window is equal to the threshold, the SS threshold, which is slow start threshold, 10 plus 3 duplicate acknowledgement. This means the congestion window in this case would be congestion window would be threshold, which is 10 plus 3 duplicate acknowledgement, 3, which is 13. So 10, 11, 12, and 13. So this means we'll be sending how many number of segments? 13 segments, waiting for a cumulative acknowledgement. And upon receiving the cumulative acknowledgement, we will increase it linearly, and we'll keep doing this. We will keep performing this congestion avoidance phase until we receive an acknowledgement for the new data. This is very important point for you to understand, right? So we'll keep doing this until an acknowledgement for the new data has been received. If it is not received, we'll keep doing it. And let's assume that at this point we receive an acknowledged or we have received an acknowledgement for a new data or new segment. Now we'll come back to this threshold, slow start threshold. And what was this slow start threshold? The slow start threshold was and is 10 in this case. And then we'll again have this linear increase, and we'll try to probe the network performance. Okay. So by the way, this here is representing what? Fast recovery phase, right? So this was proposed by Van Jacobson and is part of TCP Rto. But there's a problem with this approach. It's good to handle a single segment loss. Right? If we have this TCP Rto is not effective in case of multiple segment losses. So if we have multiple segment losses, probably this won't work. And in case of multiple segment losses, we make use of TCP Rto, new Rto. The solution to this problem is TCP new. Right? This is another variant. Let's try to understand this with the help of an example here. Okay. So So let's assume that there are, let's try to understand first the problem with TCP Reno, right? So talking about the problem with TCP Reno, right? And yes, we know the problem is multiple segment losses. Okay, let's try to understand this with the help of an example. Let's assume that I have a machine A, and there is another machine B, and it's the timeline increasing downwards. So if a packet segment is transmitted to machine A, say segment number 1, this is the timer by the way, increasing downwards. So segment 1 was transmitted, but segment 1 has lost. Then we transmit segment number 2. Then we transmit another segment, say segment number 3, and then we transmit another segment, say segment number 4. So what this machine will do is, this machine B will generate triple duplicate acknowledgement. Say okay, fine. Say okay. Upon receiving this, it will say, I'm looking for segment number 1. Send me segment number 1. Send me segment number 1. So these are triple duplicate acknowledgements. So upon receiving these triple duplicate acknowledgements, what will happen? Yes, you're right. This will enter into fast retransmit mode. Not only in fast retransmit, but it will also start fast recovery. Okay, so what it will do is, in TCP Reno, in fast retransmit, what it will do is that it will immediately, upon receiving these 3 duplicate acknowledgements, it will immediately transmit segment number 1, and it will not wait for the expiry of the RTO. So here we have retransmission timeout, right? The machine is waiting to expire in order to automatically restart or resend this segment number 1. So without waiting for this RTO to expire, the sender will immediately start this segment number 1. Okay. So this was an improvement proposed by TCP Reno, right? Acceptable. But let's assume another scenario where we have multiple segment losses. So we have a machine A, and then we have a machine B, and this is the timeline increasing downwards, and it transmits segment number 1. Segment number 1 has lost. Then it transmits segment number 2 received, segment number 3 lost, segment number 4 received, segment number 5 received, and let's assume segment number 6 lost. So this is a case where we have multiple segment losses, right? Where we are not losing single segment. Multiple segment number 1 has lost, segment number 3 has lost, segment number 6 has lost. So what TCP Reno will do in this case? TCP Reno. Okay. So upon receiving this, this segment number 2, it will generate an acknowledgement, a duplicate acknowledgement for segment number 1. Duplicate acknowledgement for segment number 1. Duplicate acknowledgement for segment number 1. How many number of duplicate acknowledgements? Yes, triple duplicate acknowledgements. And immediately upon this receiving this triple duplicate acknowledgement, the sender will retransmit segment number 1. Okay, and obviously by retransmitting in segment number 1, it enters into it enters into it enters into fast recovery mode. But as soon as it receives an acknowledgement for the next segment, which is what? Yes, you're right. Upon receiving it, it will send acknowledgement for segment number 3. Means what? That it has received segment number 2, which is what? Which is the new data that has been acknowledged. So this is the new segment. Acknowledged. Immediately upon receiving the acknowledgement 3, the TCP runner will exit this this fast recovery mode, right? And that's why it fails in addressing the multiple segment losses. And this is happening because of partial acknowledgement. Partial acknowledgement. So this acknowledgement here, 3, is called partial acknowledgement. Why? Because it is not taking care of all the other, all the other lost segments here. Okay, for example, segment number 3, segment number 6, and the solution to multiple segment losses is proposed in TCP new runner. And so the solution is very simple. The TCP new runner implements fast retransmit phase, whereby a non-duplicate ACK takes TCP out of fast recovery only if the non-duplicate ACK is greater than equal to the sequence number sent out before detection of loss. Very simple. So the solution is very simple, right? So it avoids the partial acknowledgement. So anything that is so if a non-duplicate ACK is less than this sequence number, or let's say we call it senders I, is called a partial acknowledgement. let's try to understand the implementation. We will only exit this fast retransmission if we receive um, if we receive an acknowledgement that is greater than the last sequence number that was transmitted before receiving this duplicate acknowledgement, right? So what was the last sequence number in this case? Yes, 7 or 6, right? So it's non-duplicate acknowledgement. It's only if I receive an acknowledgement, say in this case 6, then I'll exit in this from this fast recovery mode. So anything less than 6 is partial acknowledgement. Okay, for example, in the first case, in the case of TCP Rto, upon receiving this, to TCP Rto aborted this fast recovery mode. Why? Because 2 is less than 6, and this is what partial acknowledgement. So what TCP Rto does is that it implements fast transmit phase and only exits a fast recovery mode if the non-duplicate acknowledgement is greater than the sequence number sent out before experiencing a loss. Okay, so this is known as TCP Rto. And there are more variations of TCPs available. For example, in order to control this retransmission, we also have this TCP Selective Acknowledgement. So we have TCP implementation with selective acknowledgement. By the way, let me make it clear. Let's go back to the slide. So when we experience a timeout, or when we maybe upon receiving triple duplicate acknowledgement, we enter into a fast retransmit mode. The mechanism that this TCP Tahoe or TCP Rto or new Rto is following is go back and so here it has to go back to and to transmit unnecessarily the correctly transmitted segments, or it has to wait for 1 RTT in order to retransmit a segment. Okay, so there is a solution to avoid this problem with TCP Tau, TCP Rto, and TCP new Rto. What is the problem? The problem is, in all these cases, either I will be retransmit a segment after waiting for 1 RTT, or I'll go back and will retransmit all the correctly retransmitted segment, means go back. And then we have covered this go back in the previous lectures. Okay, so the solution to this problem is TCP selective acknowledgement. So SX stands for selective acknowledgement. Selective acknowledgement, right? So selective acknowledgement, why this is important? Because selective acknowledgement gives a sender better idea of which packets or segments, you call it, segments have been successfully delivered. Okay. So in TCP selective acknowledgement, TCP does selective repeat. Selective repeat instead of go back and. And yes, we are familiar with these two mechanisms that we have discussed earlier. So in order to enable this TCP selective acknowledgement, there are two options added in the options field of TCP segment. So the implementation is done by adding. So we have added two TCP options here, right? So one option, and that too by exploring the options field of TCP segment header. I hope you remember that there's an option field of the TCP segment header that we can make use of for certain implementation, and then one of the implementation is in the case of TCP selective acknowledgement. So the first option is we enable the selective acknowledgement. So selective acknowledgement permitted. So selective acknowledgement is permitted, and the option for doing this is option number 4, right? And this selective acknowledgement mechanism can be permitted only if we carry it, if it is carried only by SYN segment. So you remember whenever we need to establish a connection, we send a SYN segment. So if I want to enable or permit this selective acknowledgement rather than go back to N, so I have to use this option number 4 to permit this selective acknowledgement. And the second option that is added is called SAC option, selective acknowledgement option. That is option 5. And this enables us to send negative acknowledgement for missing segments, so that only the missing segments are retransmitted, and we are not unnecessarily retransmitting the correctly transmitted segment. So if I quickly, we can have a look at a TCP segment header. After adding these options, and if you remember, in a TCP segment header, we have source port, and then we have destination port, and if you remember, we have sequence number, and then we have acknowledgement. By the way, this is cumulative acknowledgement, okay? And then we have different fields. We have header length that tells us that TCP header is of variable length and a field is reserved. Then we have 6 flags here, okay? And one flag is set at the moment, which is the SYN flag, obviously. And then we have this receiver window size, receiver window, which is advertised by the receiver. And then we have checksum, and urgent pointer. Okay, and then we have this options field here, where there are different options available, right? And here we are talking about the option 5, right? So I'm talking about enabling option 5. It's total length. And here is, up to this, this gives us the usual, this gives us the usual TCP header. This is the TCP header if I'm not making use of TCP. So it's from 0 to 5. So if I'm not having TCP SAC enabled, this is the usual TCP segment header that I'll be dealing with. Okay, and if I enable this option 5, and I have permitted this selective acknowledgement, then next I'll be having 4 segments. Right, so here we have these are the SAC options, selective acknowledgement options, and at max I can have 4 segments, and so I'll have the first segment, and then the next. I mean, this first will give me the left side of the SAC segment, and the next will give me the right side of the SAC selective acknowledgement segment, right? And then likewise, I will have 4 similar SAC acknowledgement. First, next. Okay, so since the header length is 40 bytes of this options field, so I can have this. I can have these 4 SAC segments here. And this first, in every SAC segment gives me the left side of the selective acknowledgement segment, and the next will give me the right side of the selective acknowledgement segment, right? And by doing this, implemented selective acknowledgement, I'll be able to retransmit only the lost segments rather than all the segments. For example, if these are the packets that I have transmitted, for example, 1, 2, 3, 4 correctly transmitted, 5 has lost, 6 has lost, then 7 is successfully transmitted, 8 is successfully transmitted, 9 has lost, or maybe say 10, 11, 12, 13 number segments I have correctly received. So this means in this case, upon receiving the SAC acknowledgement, I'll first be sending only segment number 5 and 6, and then later on I'll be sending, upon receiving the SAC for 6, I'll be sending the segment number 9 and 10 respectively, and I'll not be sending any of these segments that are correctly retransmitted. There won't be any unnecessary retransmissions. Okay, and so what do you think? What is the advantage of this SAC implementation? So the question is, what do you think TCP SAC? What are the TCP SAC advantages? Yes, you're right. It decouples when and how much to send, from which to send, right? So this is very important, that it decouples the congestion control from loss recovery, and we are only retransmitting the lost segments in this case. Okay, so coming back to our slide set, the next thing that we'll be discussing is TCP timers. The TCP uses 4 timers to handle its operations. The first timer is called retransmission persistence, then we have keep alive, and then we have time weighted. And we'll start discussing the very important timer known as retransmission timer, or we also call it retransmission timeout. So let's start discussing the retransmission timer first. Okay, so first we are interested in discussing retransmission timeout. And this is also known as RTO. And remember, at the beginning of this lecture, we talked about retransmitting a segment, or identifying a congestion. This is either being done if an acknowledgement is not received and RTO has expired, or there are triple duplicate acknowledgements, right? So let's talk about the calculation of retransmission timeout. So this timer is important because automatic repeat request depends on retransmission to achieve reliability. So sender sets a timeout waiting for an acknowledgement. So if this retransmission timeout goes out, this means the sender will be retransmitting. But this retransmission timeout important. We have earlier discussed this also, that this retransmission timeout means this RTO. This RTO is computed from, yes, you're right, round trip time. Round trip time. But the problem is that the RTT varies. Means RTT of a path varies over the time. So this means we will not be having a consistent RTT, round trip time. Why? Because on a path to the destination, it varies because maybe routes are changing because of route changes. A path is changed from source to destination, obviously the round trip time will also change. Or maybe this RTT is affected because of congestion in the network. So if there's a congestion in the network, the round trip time will increase. The problem is varying round trip time complicates the computation. Number one, obviously, retransmission timeout. It complicates the retransmission timeout. We'll see in a minute how. And number two, it also affects the optimal sender's window size. Optimal sender's window size. Right? So if RTT is not stable, is changing because of the changes in route or because of congestion, this means we'll have problems in calculating retransmission timeout and optimal sender's window size. And what are these problems? Let's try to see how this can affect, how a varying RTT can affect RTO. So if let's do it with the help of example. And what we are discussing is we are discussing basically implications of a bad RTO. Retransmission. Why we will have a bad RTO? Because RTT is changing, right? So let's assume two scenarios. Let's assume a scenario where the RTO is too small. Okay, the time that a sender waits for the acknowledgement to arrive is too small. Let's see what happens in this case. Let's assume a scenario where we have a machine A, then we have a router R in between, okay, and then we have a machine B, which is the receiver, and this is the timeline increasing downwards. And let's assume the sender A in this case transmits segment number 1, and segment number 1 is forwarded by the router to the destination machine B, and destination machine B in this case generates the acknowledgement of, so it generates acknowledgement of 1, okay, and that acknowledgement is forwarded by the router. So this is what, this is one, yes, you're right, this is 1 RTT, round trip time, the time required to receive an acknowledgement of a transmitted segment. Okay, so let's assume now, upon receiving this acknowledgement 1, which means this would be a positive acknowledgement, means 2. This means the B has received segment number 1 and is now expecting segment number 2. So what will happen in this case? Now, now A will transmit segment number 2. Let's assume there is some processing delay at router, and then after some time, router forwards this segment number 2 to machine B, and machine B, generates its acknowledgement, right, which is asking for segment number 3, and now this is forwarded by the by this router to sender sender A. But here was the RTO. So this is RTT, and RTO is say slightly greater than RTT. Let's assume we'll see how it is calculated in a minute. So what's happening in this case? So after the expiry of this retransmission timeout, this sender will again transmit segment number 2. Segment 2 was rightly transmitted, correctly transmitted, and was forwarded by the router. This acknowledgement is on the way, but sender A in this case has retransmitted this segment number 2. Why? Because the RTT is small, and because we have calculated this round trip time based on this RTT. So this round trip time is small, and that's why this retransmission timeout is also too small, right? And because it's too small, so what's happening here? What's happening here? Yes, you're right. We are unnecessarily doing retransmissions. So there is no need to retransmit this segment, right? But this retransmission is taking place because this RTO is too small. So the implication of a bad RTO, the first case is that RTO is too small. We will be unnecessarily retransmitting the correctly transmitted segments. Okay, let's talk about the other case. And let's assume now that in this case, RTO is too big. RTO too big. Let's see what will happen in this case. And again, assume a scenario that where we have a sender A, and then we have a, say, router R, and then we have a destination machine, in this case, B, okay? And this is the timeline increasing downwards. And the sender A has transmitted segment 1. Segment 1 is forwarded by router 2. Destination B, and destination B has generated its acknowledgement. Say it's asking for segment number 2, and this acknowledgement has been forwarded by this router to the sender. Okay, and now this is what? This is our RTT, round trip time. Okay, and now let's assume it transmits segment number 2. Okay, and now this segment number 2 has lost on its way to destination. Okay, I mean, it has not received by the router R here. So now what is happening here? So now it's waiting for the say expiry of the retransmission timeout, and here it was the RTT, and this is our retransmission timeout. On the expiry of this retransmission timeout, it will retransmit this segment number 2. So see what is happening here. Here this RTO is too big. Because this RTO is too big, this means this will result in, yes, you're right, lower throughput. Why? Because we are waiting and waiting for our RTO to expire to retransmit a lost segment, right? So we'll end up wasting our bandwidth by not sending anything on the network. So I hope students, it's clear to you that how the retransmission timeout can be affected because of the varying RTT, and how varying RTT complicates the computation of retransmission timer. So that's why an RTO must. So that's why the time that we are interested in calculating retransmission timeout must adapt to actual and current RTT. So rather than having considering the current RTT, we also need to have the actual RTT, right? So this means we have to estimate. What do we mean by this? This means we have to estimate. We have to estimate the RTT. Okay, rather than using its current value, we have to estimate it by observing or by watching returning acknowledgements. Okay, what do you mean by this? This means we need to compute a smooth. So we need to compute a smooth estimate. And the smooth estimate can be calculated by keeping running average. Running average of what? Running average of the RTT, right? So rather than using one recent value of RTT, which is varying, which is changing, right? So what we'll do, we'll keep its running average to calculate a smooth estimate. And by the way, this running average is also known as exponentially weighted moving average. EW, right? In stats, we call it exponentially moving average. So instead of taking one value of RTT to consideration and to calculate the retransmission timeout on it, based on it, we'll have its running average, means exponentially weighted moving average, EWMA. So now, how we calculate smooth estimate or estimated RTT? So the smooth estimate, or let's call it estimated RTT, is basically estimated RTT prime is basically alpha into estimated current value of estimated RTT. So new value of estimated RTT is equal to alpha into estimated current value of estimated RTT plus 1 minus alpha into sample RTT, the recent value of round trip time. Okay, so this is how we control the variation in round trip time. Okay, by calculating its running average or exponentially weighted moving average. Here, the sample RTT is the time between a segment that is transmitted and when its acknowledgement is received. So it's just the recent value. Okay, and this new value of estimated RTT is alpha into estimated current value of the previous value of estimated RTT plus 1 minus alpha into sample RTT. By the way, this alpha is a weight here, right? So if this alpha is, let's assume 1, what does this mean? This means each sample changes by sample means sample RTT changes the estimate only a little bit, Okay, but what if the value of this alpha is 0? What do you think? What will happen? Yes, you're right. So this means each sample will influence, or each sample influences the estimate heavily. Okay, so we have to very carefully select the value of this weight, and usually it's the value of this weight is 1 by 8, or this value is 0.125. So this is the value that we use for alpha to calculate estimated RTT. So let me again repeat it. So the estimated new value of estimated RTT is equal to alpha into the current value of estimated RTT plus 1 minus alpha into sample RTT. This will help us in normalizing these variations in round trip time. The next question is, so we have estimated the RTT, we have calculated its running average, but still we have to calculate, or we have to compute RTO. So the question is how to compute, RTO. Right? So we can say that RTO is equal to, say, beta times RTT, and this RTT is, by the way, this estimated RTT, right? So let's assume typically this beta is set to 2 or 3. Okay, but there is a problem selecting or computing RTO in such a way. Why? Because in fact there are two problems here. There are two problems in calculating retransmission timeout in this way. Okay, problem number 1 is that an acknowledgement is basically the receipt of data, not the receipt of transmission. So the problem is, which packet do we need to associate with an acknowledgement? So the first problem is called acknowledgement ambiguity. First problem with the way in this, if we calculate retransmission timeout by simply multiplying 2 with this estimated RTT, the problem is there are two problems. The first problem is known as acknowledgement ambiguity, and that we'll see with the help of an example in a minute. So there is an acknowledgement ambiguity, and what is this acknowledgement ambiguity? The acknowledgement ambiguity is that which packet which packet to associate with an acknowledgement, and especially this is true when we have a retransmission in case of in case of retransmission, in the case of retransmission. So we really need to decide on that which packet will be associated with an acknowledgement in case of retransmission, right? And the second problem in calculating RTO in such a way is that this RTT or round trip times are too wide. Round trip times spread is too wide. So dear students, let me reiterate the problems, right? Explain it to you again. So up till now, we have learned that how we can normalize the variation in RTT by calculating estimated RTT, okay? And again, the problem is to compute the retransmission timeout, which is greater than RTT. And usually we can calculate retransmission timeout by multiplying the estimated RTT with 2. But there are two problems that we need to first understand, and we need to find solutions. The first problem is acknowledgement ambiguity. Let's try to understand the first problem, and then we'll see what is its solution, right? So the first problem is acknowledgement ambiguity. Okay, and the problem with this acknowledgement in the case and the detail of this acknowledgement ambiguity is that we have an original packet, and then we have a retransmitted packet. So we need to understand it with the help of two examples. And say the first case is where we have this original packet, right? And we'll see how RTO can grow unbounded, right? So the problem here is, and if I associate it with the original packet, the RTO can grow unbounded. Okay, let's see how. So let's assume a scenario where we have a machine A, sender, and then we have a machine B in this case. And again, it's the timeline increasing downwards. Okay, and let's assume that sender A has transmitted a segment, say segment 0, and segment 0 has lost. Okay, and I assume that this was the initial RTO. Okay, so so this means the retransmission timeout has expired, and now this machine A will again retransmit segment 0. Okay, and now the receiver B in this case, has replied with an acknowledgement. Okay, and now see what is this RTT now? Now this is the RTT, right? Okay, right, and it sends segment number 1, and let's assume segment number 1 has again lost. Okay, and now based on the previous RTT, it recalculates it RTO, and let's assume the new retransmission timeout is this, which is obviously greater than the previous one, and it again retransmits segment number 1. And let's assume segment number 1 has been received successfully. An acknowledgement has been generated asking for segment number 2. And now in this case, let's look at this first of all. This RTT. Now we have even greater round trip time, and so will be the RTO. So you can clearly see that the retransmission timeout with every unsuccessful retransmission and unsuccessful transmission, or with every retransmission, is growing unbounded. Okay, clear? And the second case is that the second case here is that retransmitted packets. So these were this is the acknowledgement ambiguity problem in the case where we have this original segment, the packets transmitted, and there's a loss here, and this can grow unbounded. And let's talk about the retransmitted packets. Okay. So the retransmitted packets, and this, because of this acknowledgement ambiguity, this might shrinks the RTO. So the retransmission timeout shrinks in this case. So let me repeat the original, the problem with the original packet. Where is the acknowledgement ambiguity? So the ambiguity is this acknowledgement is either for this transmitted segment or its retransmission. There's a problem. We're unable to associate this acknowledgement, right, either with its retransmission or with this actual transmitted segment. So this was the segment 0 originally transmitted, and this is its retransmission. So this acknowledgement that is giving me RTT is creating this ambiguity. Why? Because I'm unable to associate either its actually transmitted segment or retransmitted segment. Okay, so let's talk about the second case. The problem with acknowledgement ambiguity that is associated with retransmitted packets, and in this case RTO will shrink. Let's see how. Let's again assume that we have a machine A and then we have a machine B here, and this is the timeline increasing downwards. And let's assume the sender A has transmitted segment 0, right? And then again it there is a delayed acknowledgement. Acknowledgement was generated by machine B, but the RTO has expired in this case. So this is the RTO. So what will happen in this case? Machine A will retransmit segment number 0. Okay. Now, so what do you think? What is the next RTT? Either the RTT is this one, or the RTT is this one, right? Now we are associating acknowledgement with the retransmitted packets. So, and in this case, because this acknowledgement time between this retransmitted segment 0 and this acknowledgement is short, so this will shrink. This will shrink the retransmission timeout. Oh, so next time it retransmits segment number 1, and look at the waiting time. It is smaller. Why? Because it is calculated based on this retransmission round trip time, which is for the retransmitted segment number, which is segment number 0 in this case. right? So again, this will keep going on, right? And then again, will be, we have this acknowledgement, but it has expired, and next time even this RT value is smaller. Okay, right. So because of this ambiguity, this acknowledgement ambiguity, either the RTO can grow unbounded if I'm associating this acknowledgement with the original packet, or if I'm associating this acknowledgement with this retransmit segment, the retransmission timeout will shrink. So this means there is a feedback. There is a feedback loop between RTO computation and round trip time estimate. Okay, so this is the problem number one, right? That was acknowledgement ambiguity, right? Means which packet to associate with an acknowledgement in the case of a retransmission. So if the acknowledgement is associated with actual original packet, the retransmission timeout can grow unbounded, and if the acknowledgement is associated with retransmitted segments, this will result in shrinking of retransmission timeout. Okay, so this was the first problem. What is the second problem with this RTO calculation based on RTT? That is round trip time spread too wide. So the second problem is round trip time too wide. So the second problem is RTT has spread is too wide. And what do you mean by this? So the second problem is RTT's spread is too wide. So let's assume if I have this probability distribution function and I have this plot representing the different round trip times, and let me assume that here we have this RTT mean value, and here is the RTO that we are calculating, and we said this RTO is equal to RTT. Okay, and so this means, by the way, here we have probability distribution function, and here we have this. This x-axis represents the RTT samples. Okay, so this means all the RTTs or the packets with these RTTs must be retransmitted. So all the packets with these RTTs must be retransmitted. Why? Because the retransmission timeout ends here. This means all the packets after the retransmission timeout, which is 2 times the RTT, will be retransmitted. So this means because this RTT spread, do not take variance into consideration, right? So we'll see in a minute what is a solution. So let's talk about the solution of these two problems. So first talk about the solution of acknowledgement ambiguity problem. Right? And the solution to acknowledgement ambiguity problem is Kahn's algorithm. what Kahn's algorithm says, very simple. It says adjust RTT estimate only from non-retransmitted samples. So remember, what was the problem in acknowledgement ambiguity? The problem was either we have to associate the acknowledgement with the originally transmitted segment or with the retransmitted segments, right? So the solution is, according to Kahn's algorithm, the solution is adjust RTT estimate only from non-retransmitted samples. Okay, but there is another consideration that we need to make here, right? That is, if we do not take into consideration the retransmission, this could lead to insensitivity to long delays. So the problem only considering this is, however, ignoring retransmissions could lead to insensitivity to long delays. And we have seen this in this example where we try to, associate the acknowledgement with the original packet. So in this case, the RTO was drawing unbounded. Okay, so we have to keep this into consideration. So this means how we will, handle this retransmissions then. So this means we need to back off. We need to back off RTO when upon a retransmission. So whenever there is a retransmission, we need to back off the RTO, retransmission timeout. How we will back off the retransmission timeout? It's very simple. So in case whenever there is a retransmission, the new value of retransmission timeout new is always equal to 2 into retransmission timeout, previous value of retransmission timeout. And this is only the case when we are having retransmissions. Okay, so in order to cater the retransmission. So what about the second problem? What was the second problem? Yes, you're right, that RTT spread too wide. Too wide. This means what? This means RTT is not considering variance into consideration, deviation into consideration, right? Because RTT estimate is computed. Why this is so? Because RTT estimate is computed using exponentially weighted moving average. Okay, if you remember here, we've calculated it. Yeah. So this is based on exponentially weighted moving average. Okay, so that's why it only considers. Yes, you're right. It only considers the mean, and here is the problem, right? What is the problem? The problem is that it doesn't take variance into consideration, variance into account. Okay. Okay. So clearly we have seen this in this example. So the RTT is based on 2 times the estimated, RTO is based on 2 times the estimated round trip time. This is the mean, this is the RTO, and this means all the packets having RTT more than this RTO will be retransmitted. Why? Because it's not taking into consideration the variance. And the solution is Jacobson's algorithm. Solution is proposed by Van Jacobson. So Jacobson's algorithm. What it says estimate deviation of sample RTT. So we have to estimate deviation, variance. We have to estimate deviation, say D, of sample RTT. So sample RTT will be calculated in the same way that we have done earlier, right? There's no change in calculating sample RTT. But now, in order to control its spread, the RTT spread, we need to estimate its deviation, right? And this can be calculated. It's very easy. The deviation, say, is represented by this d nu is always beta into d old. Plus 1 minus beta into sample RTT minus estimated RTT. So first remember, there's no change in the calculation mechanism of sample RTT. It's the same, right? That we have covered earlier. Let me show it to you again. So the sample RTT will be calculated exactly in the same way, okay? But in order to control or calculate or estimate the deviation, so we'll calculate deviation nu by using this formula. D nu is equal to d beta into d old plus 1 minus beta into the sample RTT minus the estimated RTT that we have calculated in the previous step. And the value of this beta is 0.25. Okay. Right. So this will give me what? This will give me deviation of sample RTT. And now I will take the deviation into consideration to calculate the RTO, retransmission timeout. So we have to take the deviation in sample RTT, that is D into count when we have to compute, and computing retransmission timeout. So finally the retransmission timeout is equal to estimated RTT. And remember, say it again, remember this simple STTM, this simple, remember this estimated RTT is calculated as usual, right? Plus 4 times the deviation, okay? So this is how we calculate the retransmission timeout. Now this retransmission timeout takes into consideration not only the varying RTT by calculating this estimated RTT, but it also takes into consideration the deviation by calculating this deviation in sample RTT into consideration using this formula, right? So this is how retransmission timeout is calculated. So let's go back to the slide set. So let's talk. So we were talking about the first timer, which is the retransmission timeout. This retransmission timeout is known as retransmission timeout (RTO), and this RTO is calculated based on RTT. And the problem here is that RTT is variable, so we have to calculate estimated RTT, or you can call it RTT smooth. And this is alpha into RTT plus the current value of RTT smooth plus 1 minus alpha into RTT measured or sample RTT, right? And here the value of alpha is 0.125, okay? And usually when we calculate RTO, retransmission timeout, so we multiply it with the smooth whenever we have to calculate this RTO. So we multiply 2 with this smooth RTT or estimated RTT, right? So we have covered this in detail, that if we have to take into consideration the variance, we have to look at this the new formula for the calculation of retransmission timeout. Okay, the next timer that TCP makes use of is called persistence timer, and this timer we have already covered in the previous lecture, because this timer is used by the sender to send a probe message to the receiver machine to see if there's enough space available in the receive buffer. Remember, in order to deal with the silly window syndrome, we use this mechanism where we want a sender to advertise a 0 window size, a receiver to advertise a 0 window size. This means sender will stop sending and wait for the acknowledgement, but this can obviously result into some sort of deadlock, where the sender waits for acknowledgement and the receiver is waiting for the data. So in order to resolve this deadlock, remember, we used a persistence timer, where after 60 seconds, the sender will send a probe message to the receiver to advertise its receive window size. Okay. So the next timer that is used by TCP is known as keep alive timer. The keep alive timer is used to prevent TCP connections to exist forever. So there may be a case where a client connects to a server, transmits some data, and then crashes. But on the server side, the connection is still there. All the buffers and the variables are being maintained by the server. So normally server gets a keep alive timeout after two hours. So after keep alive timeout, server probes the client, and if client is not there or has crashed, there's no response from the client, the connection is terminated. And then the last timer is called time-weighted timer. This time-weighted timer is used to terminate a connection. So whenever we have to terminate a connection, so TCP sends our connection close request. The connection is held in a limbo for time-weighted period, allowing the duplicate FIN segment to arrive at the server side. Right? The value of the timer is usually twice the expected lifetime of a segment. So upon receiving the duplicate FIN, which is for this duplicate FIN, we wait for time-weighted timer. Okay. So with this, I would like to conclude today's lecture. So basically, so we have talked about TCP congestion control mechanisms, in which I'll talk about the regional TCP, where congestion control mechanism in original TCP, where there was only loss recovery, and loss recovery was dependent upon the retransmission timeout. Okay, and then we talked about TCP Tahoe. TCP Tahoe has this slow start and linear increase mechanism, and it also has fast recovery, a fast retransmit, where the 3 duplicate or triple duplicate acknowledgement indicates a loss of a segment, right? So we again slice the window size by 2 to determine the slow start threshold, and then we go into the slow start phase and resend the lost segments. Then we talked about TCP Reno. TCP Reno has this fast recovery, but it also includes the the fast recovery with the fast retransmit. But the problem is that if we have multiple segment losses, this will not help us. And the solution to this problem was given by TCP New Reno. In TCP New Reno, we have implemented fast retransmit phase, whereby a non-duplicate acknowledgement takes TCP out of fast recovery only if the non-duplicate acknowledgement is greater than or equal to the sequence number sent out before the detection of the loss. Means we have to ignore a partial acknowledgement in this case. And then we talked about the different different estimates for the that affects the TCP performance. We talked about the round trip time estimate. We talked about the retransmission timeout computation, and then all the other variables that are maintained in the calculation of TCP congestion control or the TCP variance. And we also talked about the persistence timer, time-weighted timer, and keep alive timer. This concludes our today's lecture. Dear students, thank you very much. Allah Hafiz.